Hello everyone, my name is Jie Zhang from KAIST. Today I will talk about our work DRAMless, which is hardware acceleration of data processing with no memory. Firstly, I will use a single slide to summarize this presentation. Traditional heterogeneous system employs accelerator and storage as discrete device. Data initially received in the storage but should be processed in the accelerator. A memory hierarchy is introduced to move the data from the storage to the accelerator. It contains multiple layers, including the host side memory and accelerator side onboard memory. Data should be firstly copied from the storage to the host side memory. Once the data is available in the host side memory, the data is then moved to the accelerator side memory. Afterwards, the accelerator side's core are able to process the data. Such data movement can be the performance bottleneck. To address the challenge, we propose DRAMless. We firstly design a real PRAM-based memory subsystem. It can accommodate all the datasets. We then integrate the PRAM-based memory subsystem into the accelerator. The accelerator can directly access data from the PRAM as memory. Our evaluation results show that DRAMless can improve the performance by 47% and reduce the energy consumption by 81%. Next, I will talk about our motivation and challenges. Nowadays, we are generating a large amount of data. For example, YouTube generates 300-hour new videos per minute. Instagram uploads 100 million photos in a day. To process such large amount of data, there is a high demand for high-performance computers. Accelerator can be a good candidate to accelerate the data processing. Compared to a traditional CPU, accelerator usually employ a large number of cores. This is a great chance for the parallel computing. By processing the massive data across multiple cores in parallel, the accelerator also can deliver higher computing powers than the traditional CPUs. However, the traditional heterogeneous system, which includes the accelerator and SSD, can face multiple challenges. Here is a single architecture of the heterogeneous system. The storage and accelerator are discrete devices which are connected to the host. Before the accelerator can access data, we need to move the data from the storage side to the host first, and then move the data from the host to the accelerator. During this procedure, the host needs to handle multiple software works. For examples, we need to create the file descriptors for the read and allocate the virtual memory. We also need to allocate the coprocessor memories for the new incoming data. We then need to request the file reads and allocate physical memory. Afterwards, we need to generate the request for the data. The host then can transfer the data from the host side to the DRAM and transfer the data from the main memory to the accelerator. Once the results are returned from the accelerator, the host also needs to handle multiple software works. For example, the host needs to request the file writes, and then it allocates physical memories and copy the data. Afterwards, it transfers the data. Once all the data transfer has complete, the host also needs to release the memory and release the internal memory of the accelerator and delete the file descriptors. So data movement in the traditional heterogeneous approach can introduce redundant data copy, software intervention, and data transfer overhead. The data movement overhead can introduce huge performance degradations and energy consumptions. We compare the performance and energy of a heterogeneous system and an ideal system. We assume that ideal system has all data in the accelerator, which does not need data movement. As you can see from the left figure, the performance of heterogeneous system actually degraded by 38% compared to the ideal system. You also can see the energy consumptions between the heterogeneous system and the ideal system. As you can see from the right figure, the energy cost of heterogeneous system actually increased by 5.2 times compared to the ideal system. To address the challenges, we propose DRAMless. DRAMless is a new accelerator hardware platform. It can eliminate the software intervention from the host, remove the data movement overheads, and can provide the environment for the flexible computation. Compared to a traditional heterogeneous system, we introduce PRAM and the storage media. PRAM can provide large capacity and to accommodate all the datasets. Our DRAMless implement a real PRAM-based memory subsystem and integrate it in the accelerator. All the cores in the accelerator can directly access data from PRAM subsystem as memory. Next, I will talk about the overall design, including the hardware platform and the program model. Our accelerator platform includes 8 cores. 7 cores works as agent to process the kernels. The last core works as a server to coordinate the kernel scheduling. It also employs MCU to manage PRAM access. All the cores are connected through a crossbar network. Our platform includes register sets to manage the status of the platform. It also includes a PCIe module to interact with the host. We also attach our PRAM-based memory subsystem to the crossbar network. They can directly replace the traditional DRAMs. The figure is the traditional heterogeneous system that I mentioned before. In traditional heterogeneous system, the host needs to prepare both data and the kernel for the accelerator. This can introduce high system overhead, redundant data copy, and long data transfer. As we can store all the data in the accelerator side PRAM, our DRAMless only need to prepare the kernel, which can simplify the procedure. The host first generates the compute kernel. It then groups the kernel into a package and downloads the package to the unused PRAM space. The server in the DRAMless will take over the remaining task. It will pass the package to extract the kernels and schedule the kernels to the agents. The agents then will process the assigned kernels. Next, I will talk about our implementation of the PRAM subsystem. Our PRAM subsystem includes a FPGA-based controller and multiple PRAM banks. Each PRAM bank builds a PCM array. Each cell of the PCM array includes a diode and a storage core. The storage core can change its resistance by hitting the GST. A set operation can change the GST to the crystalline phase, which makes the storage core in low resistance. A reset operation can change the GST to amorphous phase, which makes the storage core in a high resistance. We can use the set and the reset operation to program bit value 1 and 0 into the storage core. A read operation is to sense the resistance of the storage core. As the read operation does not change the structure of GST, it is much faster than the write operation. The PCM array is organized as 16 partitions. The multi-partition architecture of the PCM array allows parallel access in different partitions. We will explain how we can benefit from these new features in short. The PCM array also can serve 256-bit data in parallel, which is much wider than a traditional no-interface-based PRAM module. PRAM bank has different row buffer designs compared to the traditional DRAM banks. While traditional DRAM banks employ a single large row buffer, a PRAM bank employs 4 address buffers and 4 data buffers. Each data buffer can only store 32-byte data. We can use 2 I/O pins to enable a pair of address buffer and the data buffer at a time. As the PRAM chips has a larger memory space and a limited number of I/O pins, we adopt 3-phase addressing to access data. Specifically, a row address is split into the upper address and the lower address. During the pre-active phase, the upper address is stored in the address buffer. In the next activate phase, the lower address along with the upper address, which is stored in the address buffer, will be passed to the row decoder of the PCM array. The data of a row will be fetched from the PCM array to the data buffer. Lastly, in the read and the write phase, a colon address is used to select specific data in the data buffer. One of the challenges in PRAM is the long write delay. Solving the write request can block the whole PRAM array. To address the challenge, our PRAM evaluation module introduced a non-blocking write management with new hardware components, which are overlay windows and the program buffer. The overlay window is a set of registers to control the write operation. The registers store the command code, the request address, the execution command, and the status of the execution. The program buffer is a 1K register, which is used to store the write data. Once we correctly set the register in the overlay window, PRAM module will automatically write the data from the program buffer to its PRAM array. While we are waiting for the write operation, we can leverage multiple partition structure for the parallel access. Specifically, we can issue another read operation to other PRAM partition in parallel. This design can make sure read requests are not blocked by the write request. To simplify the access of overlay window, we map the overlay window to PRAM address space, so we can use the three-phase addressing to access the registers. The main task of a PRAM controller is to translate I/O commands, manage PRAM internal resources, and control I/O transactions. It is essential to process massive incoming requests in a timely manner. We use the traditional SSD firmware as a PRAM controller. However, the traditional SSD firmware has relatively low performance, which can introduce high overhead. We compare the performance of employing SSD firmware and employing an ideal PRAM controller. As you can see from the figure, employing the traditional SSD firmware can degrade the performance by up to 80% compared to an ideal PRAM controller. So we propose a FPGA-based PRAM controller to automate all tasks in hardware. To serve the general read and write request, our FPGA-based controller builds a translator module to convert the incoming requests to commands and address. This information are stored in the mode register and address register. We also design a memory control logic. It includes a command generator to handle three-phase addressing and manage the I/O transactions. Lastly, our FPGA-based controller creates a data path to deliver the data between the L2 cache and the PRAM banks. Our PRAM controller can optimize the read performance. It leverages the multiple address buffers and the data buffers to interleave the multiple read requests. Here are the examples. Let's assume there are two read requests, request 0 and request 1. Request 1 fetches the target data from the PRAM array to data buffer through its pre-active phase and activate phase. Our PRAM controller does not continue the read phase of the request 1. Instead, it runs the pre-active phase and the activate phase of request 0. While we are waiting for 8 nanoseconds of the activate phase, our PRAM controller can execute the read phase of request 1 in parallel. This design can parallelize the three-phase addressing of request 0 and request 1. Afterwards, our PRAM controller can execute the read phase of request 0. Our PRAM controller also can improve the write performance. The key technique is selective erasing. Here are the examples. Let's assume there are multiple write requests. Serving the write request is to overcome the data in PRAM cells. The override process firstly needs to reset the whole PRAM data blocks to 0 value. It then programs 1 values to PRAM cells by using a set operation. Each override process will take 18 microseconds. An erase operation can reset multiple PRAM data blocks to 0 values. If we can erase the target PRAM data blocks in advance, we can avoid the reset operation and reduce the write latency to only 10 microseconds. However, the erase operation can consume 16 milliseconds. The low latency is difficult to hide. We propose selective erase. We can speculate which PRAM data blocks will be overwritten. For example, when the kernel allocates memory space, we can reset only the allocated PRAM region by writing 0 values. When serving the incoming write request, the write latency will be reduced to the set operation latencies. We evaluate the performance of our proposed read and write optimizations. As we can see from the figure, by interleave the read request, we can improve the overall performance by 12%. Selective erasing can improve the performance by 54%. This is because write latency is much longer than the read latency, so write optimization has greater impact on the performance. Lastly, combine the read optimization and the write optimization can improve the performance by 77%. Next is our evaluation. Our hardware platform uses 8 cores, each running in 1 GHz. The read and write latency of our PRAM bank is 80 nanoseconds and 10 to 18 microseconds. We use a polybench as our evaluation workload. Our PRAM memory modules is shown in the table. We use LPDDR2 NVM timing diagrams. We evaluate different potential accelerator designs. The first configuration is a heterogeneous system using the SSD and accelerator as discrete device. We use SSD and the PRAM as storage device. The second configuration is to integrate flash-based SSD and the PRAM-based SSD in the accelerator. It still needs DRAM as buffer. The third configuration is to integrate a NOR-based PRAM in the accelerator. The NOR-based PRAM is an old model. The last configuration is our DRAMless. We compare the performance of different accelerator configurations. We first compare the heterogeneous system and our DRAMless. Heterogeneous system suffers from the high data movement overheads. We then compare the legacy PRAM and our DRAMless. Legacy PRAM uses a NOR interface, which has really narrow bandwidth, so it has much lower throughputs compared to our PRAM samples. We also compare the integrated SLC, MLC, and TLC, which is integrated into the accelerator. As these configurations still need to move the data between the NAND flash and DRAM, so it exhibits poor performance compared to our DRAMless. We also compare the traditional SSD firmware and with our DRAMless, which is based on the FPGA. Traditional SSD firmware introduces high overhead due to the low computation powers, so it also degrades performance compared to our DRAMless. Here's the conclusion. Processing explosive increased data size requires heavy usage of coprocessor. However, the long data path between the storage and the coprocessor causes huge performance overheads. We propose DRAMless. DRAMless is an approach which integrates non-volatile memory chips into a multi-core coprocessors. It eliminates the software intervention and the redundant data copies. It also provides fully computation flexibility. The evaluation revealed that the DRAM improved the performance by 47% compared to the traditional approach. It also consumes only 19% of energy compared to the traditional approach. Thank you very much. I'm willing to have your questions.